welcome to my first ever video on my YouTube series, Detective Files. Today, we are looking at British serial killer Harold Shipman, or as some people may know him, from his nickname of Dr. Death. So, the first question in everybody's mind would be, who is Harold Shipman? Now, Harold Shipman was a general practitioner within the UK. He worked within the town of Hyde, which was located in the Greater Manchester area, at Donnybrook Medical Centre. He was also a serial killer, though, who murdered many of his patients and even forged the will of one of his patients. So, the way he would murder his victims would be by giving them high, lethal doses of a drug known as diamorphine, where he killed many of his patients. However, was only sentenced to 15 concurrent life sentences due to how the police couldn't actually tie him to most of the murders that he probably did, as it is assumed that he did up to 200 of his patients with the crimes he committed, and what most of them were elderly women. So, going into the detail on the drug that Harold Shipman used, it was a drug known as diamorphine, which is a very dangerous substance and is illegal unless you have special permission to do so, like he had as being a doctor within the UK. So, the way this affects the body is by binding to the opioid receptor cells within the body. This causes a multitude of effects, such as reduced pain, which is why it's used as a painkiller within the medical realm. However, it does also cause decreased heart rate and respiration, as well as blood pressure, which, if all fall too low, will be extremely fatal. So, what we'll do now is we'll look into how the police may have actually detected that diamorphine was used within the crimes that took place. First things first is looking at gas chromatography and mass spectroscopy. So this is the first possible technique that may have been used within the Harold Shipman case. And it also is known in the world of forensics as GTMS for short. So the way this works is by the solution, which in this case would be the diamorphine, is split apart with a carrier gas, which could be anything from like hydrogen or maybe even helium. And they can do this by, for example, having urine as a sample, but it could also be blood or other bodily fluids. But going with urine for this example, once it's been put into a container of a 12 milliliter vial, a lot of chemicals will get added to it, especially the ones that will be deemed most applicable for that bodily fluid. And once that's been done, it gets heated up and gets exposed to all sorts of fibers, especially one that's been covered in something called PDMS or polydimethyl siloxane. And then, as I said before, the carrier gas will split it apart, normally helium or hydrogen, and due to it being a possible compound, it splits it all apart, so the heavier chemicals will move slower. This is due to something known as retention times. Now, when it exits the gas chromatogram and goes into the mass spectrometer, due to them all going in at different times, the mass spectrometer analyzes all the chemicals inside, mainly by having them done as ionized fragments, which then looks at something known as the mass to charge ratio, which is what is used to be able to detect what's been passed through. And then the next one from GCMS is looking at something known as ion mobility spectroscopy, which is very similar to GCMS. However, this one is a non-destructive technique. You might see this be done by law enforcement as well as also airport security. So this does have two uses. The way it's done is the sample is put through the device in a completely different manner, as when the ions are put through the carrier gas, they move at different speeds. However, instead of looking at that mass to charge ratio that I spoke about prior in GCMS, the ion mobility spectrometer will actually look at the charge of the ion, as well as the reduced mass and the collision cross section of the ion that has passed through it. So then, apologies there. Furthermore, as the name does suggest, the sample must be ionized. So the device, the way that this works for the device is by something known as electrospray ionization, or it could be radiated by sorts of radioactive substances. So then there are two types of ion mobility spectroscopy as well, with one being drift tube ion mobility spectroscopy, which follows the process that I've explained, and even uses the time taken for the substance to reach that detector to be able to get a better idea of what chemicals may have been used. And then the second one being high field asymmetric waveform ion mobility spectroscopy, which uses a very strong electric field to manipulate the ions a little bit and get them through like a filter, which is able to be a little bit more accurate as it's able to select the ions that it needs. And then finally, moving on to Raman spectroscopy, which is probably, in my opinion, the least likely to have been used. However, it is a possibility, where it uses a laser, which is then shot through the substance, which is then scattered apart into two parts, which is elastic and inelastic. Which then, during this process, the molecules that are being targeted might have gained a little bit of energy or lost a bit of energy from the light due to the different wavelength. So what it does is it then looks at that new wavelength, and since different chemicals will change the wavelength by different amounts, it kind of gives an idea of what chemicals will be inside it, as one may increase it by a very small amount, but others will also decrease it. And it can actually be built up upon, as you can get an extra piece of equipment added upon it, which is a near-infrared excitation, which has been used before by many different people. And this is more used to try and find different chemicals inside it due to impurities, as sometimes the Raman spectrometer can't handle it very well when it's very impure, but with this piece of equipment, it does find better with dilutants and filtrants. So, going over my thoughts and looking back upon this case, as I said, GCMS is the most common. Therefore, in my personal opinion, I would probably say it is the most likely that it would have been used. Especially, it does provide very, very strong results, and it can also be compared if they decided to go with IMS or with Raman spectroscopy, or maybe even some other preliminary tests such as Marquis reagent. And then looking at IMS, this is also a possibility due to its very precise and simple method of use. However, it does require a pre-built database, and if the sample is not in that database, then an answer might not be gained. And then finally, for Raman spectroscopy, this is a very extremely useful method, but it is very unlikely that would have been many important chemicals inside the diamorphine that would have gave it its effects, and it probably would have just been the opioid itself that they really needed to detect. So, and with this being the first video on the channel, I do apologize for the poor value, but I hope everyone likes and subscribes to the video, and now goodbye, and keep on case hunting.